This is a Kinect's motor. It runs off of two AA batteries and has a switch to control direction. If you had Kinects growing up, you know that these could add a lot of automation opportunity to your project. Now I want to incorporate microcontrollers with the building medium, but the motor design makes this improbable. The user still has to manually actuate the switch in order to control the motor. I'm going to need to change that. First, let's see how it works. It looks like both rails on the switch are electrically isolated, so each rail can be interfaced with a different side of the motor. This effectively flips the motor orientation to the batteries depending on switch position. When the motor runs, it draws around 300 milliamps at 3 volts, but spikes to 600 milliamps when the direction changes. So we need a circuit that can handle this. The PCB measures around 10 mm by 22 mm, so we need a chip that can accommodate these dimensional constraints. A quick check of the usual suspects revealed this half-bridge motor controller. The LB1938FA by ON Semiconductor comes in a Micro 8 package. It is a CMOS chip with supply and logic voltage ranges of 2.2 to 10 volts. The typical application diagram appears to show the chip running off of the source voltage rail while the MCU only provides the control signals. Unfortunately for our application, this means the chip is always drawing power from the batteries even when the motor is not being used, so I will have to remember to disconnect the batteries. If I forget though, it's not a huge deal because the standby current is a mere 5 microamps, which assuming a typical alkaline capacity of 2500 milliamp hours, the chip will run for nearly 30,000 weeks in standby mode. I could install a switch, but with this space that would not be worth the effort. The application schematic has 3 wires leaving the IC to go to the MCU, signal ground, input 1 and input 2, and it looks like a 1x3 DuPont header will comfortably fit in the slot originally used by the switch. This solves our interface problem. This should also leave a modest level of speed control that didn't previously exist because the inputs can be PWM controlled. I will have to test that feature though in order to know the effective duty cycle range. Here I have the final schematic on EasyEDA. And here is the board schematic. I have left room around the edges for filing if needed, and the only problem I may run into is connecting the battery terminals the intended way. If the tabs cannot be made to reach the breakouts, then jumper wire will have to be run. From project inspiration to this point took a few hours. Unfortunately, I will have to wait longer for the PCB and components to arrive. This is going to be painful.